This video is for Math 1332, meant for Tuesday, August 1st, when we are covering sections 8.5 and 8.6. 8.5 is similar to 8.4 that we did last video. 8.4 was about getting interest or present or future value using compound interest. And one thing about those kind of problems, though, is that if you do the normal kind of problem where you're looking for the future value and you know how much present value you have, how much money do you want to borrow, invest right now, and do it in some kind of compound interest, those kind of problems, the payment is only made one time. One time you borrow the money or one time you invest the money. So what's the big difference in section 8.5 is 8.5 is called annuities. And it's very, very similar, except for that payments are made every so often, not just one time. Typically, at the end of each month, you make a payment. And then again, it won't matter whether you're the one trying to get money or the one that's going to give the money. The calculation's done the same either way, no matter what point of view you're on it. And then section 8.6 is related because car payments, in essence, are annuities because you pay a monthly payment at the end of every month. So section 8.5 is called annuities. Annuities are just periodic payments that involve gaining interest from a compound. And then there's methods of saving and investments, but it's all a similar type of concept here. So this problem looks very similar to section 8.4. There is the big difference first is periodic deposit. Somebody is putting in $8,000 at the end of each year. Not just one time, but every year for so many years. They're going to do it for 40 years. And then 7% compounded annually. So a good example of this is a retirement fund, although it's usually not done at the end of each year, but at the end of each month usually, or maybe even a couple of times a month out of your paycheck. But somebody could do this. They could just save money all year long and then take some of it and put it away somewhere in some kind of an account and do that. Like if they're in their 20s right now, say you're like 25 years old and you start saving every year for the next 40 years till when you're 65, then that's usually a common retirement age. And then the nice thing is you get a whole bunch of money to live off of in your retirement age, and you don't have to work a job at that point anymore. Okay, because there's multiple payments, not just one payment, the formula gets slightly different, but you'll hopefully recognize some of this from last time. So if you look at this middle formula right here, the top portion of this looks like what we did last time. So you have the A future value equals P principal or present value. But here it's actually payments. It's not just one time. And then 1 plus R over N to the NT power. That's what we had last time. So once you're told that this is an annuity or you're told that the payments are made more than once, then the formula extends out to this. There's an extra -1 here. And then there's a denominator that has R over N. Same fraction as this one. The first formula here is what if you just do it once a year? If you do it annually or once a year, then the N equals 1. And anything divided by 1 or times 1 doesn't matter. So all the N's disappear only if N is 1. But even if N's 1, you could still use this middle formula. I'm going to do that when I do this problem here that's annual. So you really don't need the first formula unless you just like, okay, if I know it's 1 year, then I'll use the shortcut formula. So you could do that if you want. But you're going to see it's going to turn into that anyway. And then the reason for this formula comes literally from the middle one by just doing some algebra until you solve for P. So sometimes you know how much you want to put in each month or each year into your retirement fund, for example. And then you want to know how much will I have when I retire. That's the more common problem. But what if you know how much you're going to want to have when you retire. What if you tell your investor or your stockbroker or whatever, your financial advisor, what if you tell them, I want to have $1 million when I retire? So that's, you're saying in 40 years, I want to have $1 million to live off of. That's the future value. So how much should I put into an account every month or every 6 months or every year? You can figure out what the payment should be. So really, it's the same formula. It's just this fraction here moves up to the top. This big bracket part moves down to the bottom. And the A and the P flip-flop with each other. So the middle one's the more common problem in this section, but occasionally they'll ask us to find what the periodic payment should be. Then we'll use this last formula over here. And again, the good thing is not only could you write these formulas down on paper, but you can always click this icon to pull them up too. So even in the middle of a test, you don't have to memorize any of these formulas at least. Okay, so I want to find the value of an annuity. That, in other words, what is it worth 40 years from now? So we're looking for the future value on this first problem. And that's the formula that has A equals, now don't get this P mixed up with the one from section 8.4, because they call that P there too, but that P is a one-time payment. This is a multiple payment. So they just abbreviate it P, even though we use that for another thing too. But then you have your usual 1 plus R over N to the NT power. If you just do that much, that's what section 8.4 is when there's just one payment. As soon as you know it's an annuity, if they say annuity or if they mention there's multiple payments, then you know to keep going. And there's an extra -1 at the end of that. And then the same fraction here goes in the denominator. In my problem 1, I'm doing $8,000 at the end of each year. That's my payment, yearly payments. So it's not going to happen once. It's going to happen 40 times actually. And then 1 plus R over N. R is this 7% compounded annually. Annually makes N equal 1. So you can just use the main formula and put a 1 here if it's annually. And then remember how you repeat that 1 right here for this end. These two ends are the same. And then we're doing this for 40 years. And then the denominator has the same fraction, 0.07 divided by 1. Well, very similar to section 8.4, it's probably best if you do the exponent first, which usually is easy or can be done in your head. 1 times 40 is 40. So I always get that out of the way right away. And then the second thing is to get the fraction done. But the good news is the denominator fraction is the same as the numerator fraction. So whatever it is for one of them, it's the same for both of them. And this is the point of why there's a shorter formula. Anytime you do 1 times 40, you get 40. Anytime you do 0.07 divided by 1, you get 0.07. So the times 1 and the divided by 1 don't matter. So if you realize that, you could have just used this formula, in other words. This is a shorter version of the formula, only when n is 1. So that's why they put that there. And if you like that and you knew it to do that, you could just do that. Okay, so now I have 8,000. So remember the good old 1 plus from last section? That still applies here too. So you always do the fraction to get a decimal, and then when you do 1 plus a decimal, you literally get 1 point, whatever that decimal is. So 1 plus 0.07 is 1.07. I know it's to the 40th power. And then there's a -1 here before the bracket closes. And then the denominator is just the 0.07 without the 1 in front of it. So the next goal is to get this bracket down to a single number, which will happen in 2 steps. I need to do the exponent first, and then I'm going to minus the 1. So if I type 1.07, hit my exponent raise to button to the 40th power. And I don't care what happens with this number. It is often be really a larger number than like 1 point something, it's 14.97, but it doesn't matter how large that gets. If you do something for 40 years, it's going to accumulate a lot of money no matter what the interest rate is or what's going on in the problem. But 1.07 to the 40th power, just do that first. And then there's this automatic -1 if it's an annuity. So this is the bracket part. And we don't want to round anything here. So if you try to write 13.97 down and then work with that, if you just did 13.97 times 8,000 divided by 0.07, it's going to make the answer off a little bit. So this is what's good if you have a scientific calculator. After you do that much, leave all this on the screen. And I can just quickly hit times 8,000. The 8,000's multiplied here. Times 8,000. Press equals. And then divide by 0.07. So once I press equals, this will be the part A answer. This is how much your annuity is worth 40 years from now. And it's quite a large amount of money. It's $1.5 million actually. $1,597,080 and maybe 90 cents if they want cents. But when you have such large dollar amounts, they usually go to the nearest dollar. So I'm guessing they're going to change this $80 to 81 because the 8 will make the 0 add by 1. So it's probably 1,597. $1,597,081. So this is why if you have a job, especially if you can start in your 20s, if you get a job in your 20s after finishing college, if you can start contributing to a retirement fund, it's definitely going to be worth your while. Now, many of us don't have $8,000 every year to invest. The more you invest, the higher it goes, obviously. The longer the time you do it for, the better. The higher the interest rates, the better. So certain things can make this better or not quite as good. You might not get $1.5 million over your time, but this is what it would take to have that happen. So do not round until the final answer, then round to the nearest dollar. I figured they were going to do dollar just because it's such a large amount of money anyway. Who cares about 80 cents if you're in the millions of dollars? So $1,597,081. Okay, so then we need to figure out the interest. Now, if you remember in section 8.4, the interest is always easy to find after you got part A because one time you made this $8,000 payment in section 8.4. So you would always just subtract that original P from whatever the answer was in part A. So it's not quite as easy here, but in essence, that's what is happening. But you are making this $8,000 payment multiple times. In fact, the number of times you're doing it is whatever the exponent ends up being. So for 40 years, at the end of each year for 40 years, somebody's putting $8,000 into an account as, say, a retirement fund. So they're really paying $8,000 40 different times. This is all their own money, actually. They're having to come up with this money themselves. 8,000 times 40 is $320,000. So that's maybe more money than the average person can afford, but here's why these things are so good if you can get a retirement fund like this. Because this person, maybe they have a large salary. I mean, $8,000 over a whole year, if you have like a $80,000 salary, $8,000 is only 10% of your salary. So most people can live without 10% of their salary if they are smart and invest well. So let's say this person makes $80,000 a year. That's not like a super rich job. That's is maybe higher than the average person, but it's not extremely rich. And here's the good news. They only invested $320,000 of their own money over 40 years. At the end of the 40 years, their account is worth almost $1.6 million. So this is what you subtract. You don't subtract the 80,000 like last section. You have to do the 80,000 times however many times you're doing it, which is the final exponent. But even still, this is a lot of free money. You could have just put this money under your pillow for 40 years. And you would only have $300,000. That's still pretty nice, but you could have had $1.6 million. And $320,000 of that is your own money. But all the rest is free money interest that the bank's just giving you. You're getting almost $1.3 million of free money just by having a retirement account. And that's probably, even if you're 65 years old at that point, if you're healthy and can live another 20 or 30 years, that's probably enough to live the rest of your life off of. And you wouldn't have to have a job anymore. So 1277081. So that's the only difference here, is you have to just, whatever that 80,000 is, or 8,000, whatever that periodic deposit is, you don't just subtract it once. You have to multiply by the exponent first, then you subtract it from the Part A answer. That's the big difference here. But other than that, this is very similar to Section 8.4, actually. Okay, here's maybe a more realistic for the average person. Most of us could afford $30 at the end of every month. You're talking $1 a day. Just take $1 a day and stash it away into an account. So at the end of each month, you just take $30 out of your paycheck. Most of us could do that, and we wouldn't even realize how much difference that makes. So $30 at the end of each month, that's an annuity. It says annuity, but we're doing this $30 payment more than once. That makes it an annuity automatically. That's how I know to use the slightly more complicated formula. And this is 5% compounded monthly. There's the interest rate. And do this for 35 years. So maybe this person's 30 years old when they want to start doing this. Many people in their 20s don't always plan for this stuff early enough. They might be 30 years old before they decide to have a retirement account. Because when you're young, you're still paying other bills off, and college debt is still in there probably, so you might not be able to afford that at that point. But if you get to a point where you can start affording to put some money away, this is going to be worthwhile if you do it. So let's go to the annuity formula. A equals the periodic payments or deposits. And then you have the good old 1 plus R over N to the NT power minus 1. And then I have the extra over R over N's because it's an annuity with multiple payments. So that last one was nice, $8,000. It'd be nice if we could just take $8,000 every year and put it away somewhere. Most of us don't have that kind of money lying around, but most of us have $30. So $30 is no big deal. Skip a movie every so often and put that money in an account instead. Okay, 1 plus the interest rate is 5%, compounded monthly. So 0.05, now the N's not 1, it's monthly, that's 12. So now that shortcut formula wouldn't work because N's not 1. And then we're going to do this for 35 years. Instead of 40 years, this time it's 35. This person's just starting a little bit later, and they have less money to work with, which is fine. Anything's better than nothing. And then you get another 0.05 divided by 12 here. So really just this minus 1 and this extra fraction on the bottom, that's all that makes this different from how we calculated this last section. So get the exponent done first. 12 times 35, 420. You're going to give them $30 420 times. So every end of the month, they take $30 out of your paycheck. And if you work for this company for the next 35 years, you'll have had $30 taken away from your paycheck 420 times. So we're going to come back to that in a minute, though. Okay, so I need to get this part done next, but I'm going to concentrate on the fraction actually next because it's the same here and there. Now, doing 0.05 divided by 12 is not going to come out nice, probably. 0.05 divided by 12 is going to be a long, messy, repeating decimal, probably. See? So that's going to make things trickier here. So then all I do is add 1 to it, plus 1. And then even though it's big and long and messy, I'll write a shorthand version of it down here. So I've got 30 times 1 point. So you're always going to get 1 point, whatever this decimal is. 1.0041666 repeating to the 420th power. And then the bottom has the same decimal without the 1 in front of it. So that's another nice thing, is you just ignore the 1 and put the rest of the decimal down. So at least the top of this will be okay with my calculator because I have the whole decimal here. I haven't rounded anything here. I need to raise that to the 420th power. Raise to the 420th power. And then minus 1. That's the bracket part right there. So I've got 30 times this bracket, which is this big messy decimal, and then it's divided by this other messy decimal. And I haven't rounded anything using the scientific calculator. So I got the big messy decimal on the top. I'm going to hit times 30 divided by, and then now this is the one issue, is that I had to write a rounded version of this down. So if you type 0.004166, that might not be enough decimal places since it's rounded. So just hit a bunch of sixes. 6, 6, 6, 6, 6, till it kind of gets off the whole screen there. And even though that's still slightly rounded, there's enough decimals. If you have at least 8 to 10 decimals, that's usually good enough. I did even more than 10 here, but so press equals. The only thing you don't want to do is you don't want to just like do 0.004. That's not going to be enough. So now, see, this isn't going to be nearly as good as the last one because the $30 is so much less than that $8,000. That's why this is a lot smaller of an answer. But still, $34,082, or if they want dollar, I might have to round that up to $83. Yeah, there's a 7 there, so I need to add 1 to that too and make it a 3. Your annuity will be worth $34,083 in 35 years from now. $34,083. So how much of that was your money? How much of this is interest? The amount that is your money is the 420, the final exponent, times how much you put in every month. So we just figured that off to the side somewhere. 420 times 30. This is how much you actually put into this thing. This is all your own money right here. You just did it slowly. 420 times 30. You put $12,000 into this account over the 35 years. But it's now worth 34. You're like tripling your money. You're getting over $20,000 of free money. So even though your retirement account's probably not enough to live off of, 34,000, that's not even like a year's salary, it's still 20,000 of free money. Why not take free money like that when you're retired? You might have other means of income by that point too. So if I take this is what I need to subtract. Instead of subtracting 30, you subtract this instead. That's what's different compared to last section. Because the account's worth $34,083 after 35 years. You put $12,600 in over all that time. So you just got $21,483 of free money. That's all the interest. $21,483. You're getting more free money than what you're putting into this thing. These annuities can often do that if you do it for a long enough period of time. So the longer you can do it for, the more you put in each time, that helps the most. If you get a higher interest rate, that helps, but those other two things help more actually. Okay, here's a third example of this. We're going to do 120 at the end of every 6 months, which is semi-annually. We're getting a 6.5% compounded semi-annually interest rate, and we'll do it for 30 years. What's it going to be worth 30 years from now? Okay, so the future value of an annuity is how much you put in periodically times 1 plus r over n to the nt power minus 1 all over r over n. Here's $120 at the end of every 6 months. That's, you're talking like $20 a month. So again, most of us could probably afford to do this. $120 every 6 months. I'm getting a 6.5% interest rate. That's 0.65. And every 6 months or semi-annually, that's when n is 2. And then it's 30 years for the time. And if I just did this, this would be one payment, like section 8.4. But if I minus 1 and divide by this same fraction right here, that's what turns it into an annuity, where it has multiple payments. So the exponent's easy this time. 2 times 30 is 60. Always do the exponent first, 60. Then do the fraction second, and it'll be the same fraction in the top and the bottom. It's just that the top is going to have a 1 point attached to it eventually. So this dividing by 2 isn't bad. 0.65 divided by 2 should come out not too badly. There won't be a long, messy decimal here. It's just 0.325. 0.325. Okay, so let me go back to black here. 120. So the parenthesis part here with the 1 plus this is going to be 1.0325 raised to the 60th power minus 1 all over the 0.0325 without the 1 in front. So now I won't have any issues with rounding here because the bottom came out nicely. Okay, so I got to do this bracket part next, which has 2 steps. I'm going to plus 1 so that I can get the 1.0325 on my screen. 1.0325 raised to the 60th power minus 1. That's the bracket part. And even though that's a long, messy decimal, I don't have to write it down because I can just multiply by 120 and divide by this because this was exactly 0.0325. There was no rounding in the bottom, unlike last problem. So this annuity, after 30 years, it's smaller than the last problem because $120 every 6 months is actually just $20 a month. So whoever's doing this isn't putting a whole lot of money into it, but they're still going to get a lot of free money out of it. So they don't have a whole lot of money after 30 years, but there's a lot of free money here. So 21,000, 21,000, and there's a 1 right here, so I don't have to add 1. I'm just going to leave it 467. Your account will be worth 21,467 after 30 years. 21,467. How much interest? How much free money is there? Well, we paid $120 twice a year for 30 years. We did it 60 times. 60 different times we put $120 into the account. So 120 times 60, this is our money, the money we actually put in there. We put 7,000 of it in ourselves, 7,200. So this is what you subtract to see how much of it is free money interest. So 21,467 minus 7,200. Again, you're more than doubling the money. The free money's more than double what you're putting into this thing. So you put 7,000 in and you got another 14,000 of free money. That's pretty nice. More than twice of what you were putting into it is what you're getting out of it. 14,267. 14,267 minus 7,200. 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 14,267 That's the interest. 14,267, I think I said. Yeah. Okay, I guess this is just another example. This one's quarterly. So that's really the only thing different here is if the interest rate's quarterly or if you put the money in every 3 months, which is quarterly. Because there's 12 months in a year, if you do it every 3 months, you're doing it every quarter. So the first 4 problems at least are all the same kind. They just have different time periods to work with. Oops, I forgot the bracket right there. -1 R over N. Okay, so we're going to do $3,000 every quarter. $3,000 every 3 months, which is a quarter of the year. The interest rate is 5.25% compounded quarterly. Whatever this is, quarterly, semi-annually, monthly, yearly, whatever this is the same thing. It's just another way to word it. Another way to say quarterly is every 3 months. Another way to say semi-annually is every 6 months. So there's never going to be like a units problem with where this doesn't match that, even though it sounds different. So 5.25% as a decimal, that's 0.525. And quarterly is 4 times a year, just like 4 quarters in a game. So then you repeat the 4 right there. And we're doing this for 4 years. And that's just a coincidence that both of those are 4s. -1. And then the denominator is the 0.525 divided by 4. So do the exponent first. That's easy. 4 times 4 is 16. You're going to pay this money 16 times. 16 times you're going to put $3,000 in the account. That's how much of it is your money. Okay, next do the 2 fractions that are always the same. And the top will be 1 point whatever it is, and the bottom will just be point whatever it is. Dividing by 4 isn't too bad either. 0.525 divided by 4. You like to divide by 2s and 4s, but if you're dividing by 6s or 12s, then it can get messier. Okay, so it's not the nicest decimal in the world, but at least it's not a long, messy, repeating decimal. So 0.13125. 0.13125. Okay, so what we have now is 3,000 times, the top's going to have the 1 point, whatever this decimal is, 0.13125, to the 16th power, -1, and then over the decimal without the 1 in front of it, 0.13125. So I can do this in the calculator to the 16th power, -1, then multiply by 3,000, and then divide by the decimal. And notice my calculator has the decimal without the 1 in front, so if I just hit +1, that quickly gets me the 1 in front of it without me having to retype it. So now I have the 1.013125, and I'm going to raise it to the 16th power. And that's a long, messy decimal, but I don't care because it's on the screen. And now I can just hit -1, -1. There's another messy decimal that's okay, because now I just need to multiply by 3,000. And then divide by that decimal without the 1 in front of it. 0.013125, and there's nothing rounded there. I wrote the whole thing down. So now you have $53,027 in your account at the end of 4 years. Just 4 years, you have $53,027 because the next digit's a 1. We don't have to add one. 53,027. That's the part A answer. How much is interest? Well, you paid $3,000 16 times. So 3,000 times 16, this is how much you put into this account. 3,000 times 16, oops, you put $48,000 in yourself. So notice you put most of the money in this time. But that's because 4 years is so short of a time period. The other problems had 40 years and 35 years and 30 years. Then you get a whole bunch of money back, a whole bunch of free money back, I should say. If you do it for a shorter period of time, you're not going to get as much free money. Now, you still got a lot of money, $53,000, but you actually put $48,000 into it. So most of that was your own money. So $53,027 minus $48,000. You're still getting $5,000 of free money, though. So $5,027, that's how much is free. That's the interest, $5,027. Okay, so I see what happened here now. Remember on the formulas when I pulled them up? We've been using this middle formula for the first 4 problems. In essence, this was used on problem number 1 because that was the only problem that was annually. We're now going to do this one right here. We want to know what the payment should be. Okay, see how it says question mark here for the deposit? Normally they told us that in the first 4 problems. What should the periodic deposit or what should the payment be? So what if your financial goal is to have $130,000 16 years from now? Maybe you're fresh out of college, you're 22 years old, you want to work a job for a while, maybe get married in a few years, and then save money for a while, and then maybe when you're in your mid-30s, then, okay, now I'm ready to get a house. And I want to have $130,000, pay for the house, and not have to have payments where you give them back a whole bunch of interest yourself. That's a lot of people do that smartly nowadays. So you know the future value. You want to have these amounts we were getting for these other answers, like 53,000 or 21,000 or 34,000 or even this one that was 1.5 million. The answers we were getting on the first 4 problems, that's given to us now in problem number 5. So what happens is the A and the P switch places with each other. The usual denominator goes up in the numerator. And then in the denominator is that part that was in the brackets. Through the solving of this algebraically, just things are flip-flopping. Oops. So you got the P is going to be the answer, the payments. The future value's up there. The R over N used to be in the bottom, now it's in the top. And then the whole bracket part used to be in the top, now it's in the bottom. That's the only thing different. So this isn't some brand new formula. All it is they solve for P. They took the other formula and solved for P. So somebody wants to have $130,000 16 years from now, maybe to buy a house. And they're going to get a 3% interest rate compounded annually. Annually is always nice because then N is 1. So 0.03 divided by 1. And then the bottom is 1 plus the same fraction, 0.03 divided by 1. And then in the exponent, you get the 1 again, since that always repeats these two. And then they're going to do this for, was it 16 years? Yeah, 16 years. Okay, but the process is very similar. I'm going to do the exponent first. 1 times 16 is 16. And in fact, not only is this multiplying by 1, in essence, getting ignored, the dividing by 1 gets ignored. So really, this is just going to be 0.03, and this is going to be 1.03. That's always nice when you have annually. You get to ignore the fraction parts, or the ones anyway. So here's what I have now. I have 130,000 times 0.03. I may as well just do that right now. 130,000 times 0.03. The top of this fraction will be 3,900. In the bottom, I have 1.03 raised to the 16th power. 1.03 raised to the 16th power minus 1. Now, since that's a big messy decimal, then we got an issue with worrying about if we try to write it down and type it back into the calculator, we're going to have rounding issues. I would like to do 3,900 divided by this big messy decimal. But to do that, I would have to type 3,900 divided by, and then I'd have to type that big messy decimal, which is hard to know it. So this is the case. What I like to do is I like to just do it backwards on purpose. Let's take the big messy decimal and divide by 3,900, which is the wrong answer. But if you hit this 1 over x button, that flips it around to the correct answer. And that way I don't have to write that previously long messy decimal down and then try to type it back in. So your payments would be $6,449, or maybe they want cents now too, so 41 cents maybe. I'll have to check what they want, but one or the other. It's either going to be the $49 or $49.41. If you do this every year, if at the end of every year for the next 16 years, you give them $6,400, that's a lot of money, but if you're like saving up every month for it, if you did that for 16 years, you would have $130,000, and you would get some of that money free, actually. They do want nearest dollar. Okay, 6,449. Oops. Was it 6,449? Okay. Oh, round up. I hate when they say that, because you would normally round this down because there's a 4 here. So they want me to round it up one from $49 to $50. Because I think the reason they're definitely doing that here is, yeah, 41 cents one time isn't a big deal, but if you do it 16 years and then maybe it's like multiple times a year, then that can actually be not a high amount of money, but that can be a significant amount of money that the bank's not just going to give that up for free just because it seems insignificant individually. So watch out for whether they say round to or round up. That caught me again. Round up. Round up means you automatically go up $1 even if the next digit's not 5 or higher. So $64.50, that's how much you have to pay every year. So how much of this $130,000 comes from your deposits? How much comes from interest? This is the same concept as the previous 4 problems. I'm going to pay this $64.50. $64.50 is what I'm paying every year, and I'm going to do it for 16 years. This is how much is my money. These are my deposits. This is my original money. $64.50 times 16. I'm putting $103,200 into this thing. But it's worth $130,000 at that point. So if you take the $130,000 and subtract what you're putting into it, that's how much is free money. So $130,000 minus this $103,200. I'm putting $103 into it, and the bank's giving me $26,000 of free money. So that's still a pretty good deal right there. You can get a $130,000 home, and basically you only put $100,000 into it. And then the home could be paid for too. If you do like most people buy a home and they might put some money down, but then they're paying house payments for the next 30 years. If you do that, you're going to give the bank hundreds of thousands of dollars in interest. So this is a smart thing to do. A lot of younger people are doing this now just to avoid giving away so much money. You're just basically giving your whole life savings away by doing the other way, the more common way. If somebody's in their 20s and they're like, I don't want a house till I'm in my 30s anyway, this is a smart thing to do. $103,200. They will save this money over 16 years, and then they're getting $30,000, almost $30,000 of free money and they got their house paid for, and they don't have to pay house payments then. That's a very smart financial thing to do right there. Okay, so here we are on one of these kind of problems again, where they give me an option. Which one do I would rather do if I'm an investor? The lump sum deposit, that's section 8.4 right there. Lump sum means you do it one time. So what if I compare section 8.4 to this new 8.5 where you have periodic deposits? They're both going for 10 years, and they're both getting 10% compounded annually. And would you rather have $25,000 one time to be paid or $2,500 10 times? Because that's the same amount of money you're putting into it. So for you, it's the same amount of money, but what about the interest? This really comes down to the interest now. So on number 6, first I'm going to do what we did in section 8.4. The future value will be a single payment times 1 plus r over n to the nt power. This is section 8.4 all over again. So one time I'm going to pay $25,000. I'm getting a 10% interest rate compounded annually, so that makes that 1. And we're doing it for 10 years. So 1 times 10 is 10. 0.10 divided by 1 is 0.10, and 1 plus 0.10 is literally 1.10. So if I take 1.10 and raise it to the 10th power, that's this whole part, times the 25,000. I will now have 64,840. I'm going to make this a 4 because there's a 5 here. $844. See, you only put 25,000 in, and now it's worth 64,000. You're over doubled your money by doing that. But that was a one-time payment. Now, what if I repeat this with an annuity, with a periodic payment? So, whoops, put a bracket here. R over n to the nt power minus 1, and then over r over n. And now the payments are only $2,500 because you're going to do it 10 times actually. So 2,500 times 10 is the same 25,000. And you're getting 1 plus, same, this is the same just because we're doing this for comparison's sake. All of that's the same as up here. But then there's the extra minus 1. And there's the dividing by the fraction again. But whenever it's annually, all these ones don't matter. I can just ignore them. So now I have 2,500. I'm going to have this 1.10 right here again to the 10th power. So that's what's going to happen first is I'm going to do 1.10 to the 10th power again. But now it gets minus 1. Then I multiply by the 2,500. And then divide by 0.10. 39,000. $844. That's kind of weird that they both had 844 in it. So in this example, the lump sum was the better option. And the reason why is it's getting a larger amount earlier on. They're putting the whole 25,000 in at the beginning of the 10 years. So there's this big, larger amount that's earning interest right away. By doing 2,500 every year for 10 years, it's starting off very small at first, and it eventually creates the same amount of money at the end that you're putting in. But you're getting more interest on the lump sum payment because there's more money in there earlier on. So after 10 years, how much more money will you have in the lump sum? Just subtract these two. So the lump sum gives me $64,844. the annuity only gives me 39,844. So I could have 25,000 extra dollars by doing the lump sum, but most of us don't have that kind of money lying around. Who's got $25,000 in their back pocket? Unless you're like an Elon Musk or a Bill Gates type. But if you are one of those rich people, they could do this, and basically they're getting the whole amount that they invested for free, extra. It's a free $25,000 for them. Okay, how much more interest will be earned? Okay. I think that's the same answer, but what you would normally do is in the lump sum payment, you just take the answer and you subtract the single 25,000. That's how we did those. These are the part B's of each section. So in part A, lump sum, you get your final answer and you just subtract what you paid that one time. That's how much interest there is. 39,844, which ironically is how much total you're making in this investment. In this investment, though, you take the 2,500 times 10, which is 25,000, to figure out what to subtract. So here you're only making 14,000 in free money. Still pretty good. 844. But see, if you subtract these two, it's $25,000. So I kind of had a feeling that it was going to be the same answer, which is strange, but 25,000. So that turned out to be the same. Okay, suppose you earned a bachelor's degree and now you're teaching high school. See, this is common. Somebody's just fresh out of college and now they have a job. The school district, that's another thing, that whatever job you get, sometimes the job gives you benefits. Benefits are things like retirement funds or health insurance. So school districts will do this sometimes to get teachers to work for them. The school district offers an opportunity to take a year off to earn a master's degree. And the reason they do that is then the teacher can teach dual credit classes. To achieve this goal, you deposit $3,000 at the end of each year in an annuity that pays 5% compounded annually. So this is the same as the first 4 problems. They're just doing it in kind of a realistic example here. So it did say annuity, so that's why I know to go back to this formula. So you work for a little while and then they're going to let you take time off to go get a master's degree so you can even make more money after that. And so you're going to work for the first 5 years. That's what I was looking for, 5 years. And then you get to take a year off. So the time is 5 years. You're doing $3,000 at the end of each year, and it's compounded annually 5%. So at the end of your first year of teaching, you take $3,000 out of your salary and put that in an account and do that for 5 years. And it's 5% compounded annually. So annually is when n is 1, which really means you can ignore that then. Do this for 5 years. So the times 1 and the divided by 1s are not going to matter. I have right here, you can literally see it right there. It's 1.05 raised to the 5th power. $1.05 raised to the 5th power. Then minus that 1 right there. Times by this 3,000 in front. And divide by this 0.05. So you'll have 16,577. Add 1 to this 6 and make it a 7. 16,577. and you paid 3,000 5 different times, because that turned out to be the final exponent, 3,000 times 5. You paid 3,000 times 5. You paid $15,000 out of your salary into the account, but you get the money back after 5 years. So you get your $15,000 back plus about $1,500 in free money of interest to help pay for that. So 1,577 is just free money. So after 5 years, you'll have 16,577 in your account, of which 15,000 of that was your own money. So the interest is 1,577. Who wouldn't want 1,500 free money? Okay, to offer scholarships to children of employees, a company invests $15,000 at the end of every 3 months in an annuity that pays 9% compounded quarterly. Same kind of problem, just trying to do it in a realistic situation. So future value of an annuity is your periodic payments times 1 plus R over N to the NT power minus 1 all over R over N. So they're going to put $15,000 every quarter, and they're getting 9%, 0.09. Every 3 months is the same thing as quarterly. So notice it says compounded quarterly and it says every 3 months. That's the same thing. There's 3 months in a quarter of a year. So quarterly is when N is 4. And then they're doing this for how many years? 10 years. So do your exponent first as usual. 4 times 10 is easy, 40. Do the fraction second. Luckily, divided by 4 doesn't make it too messy usually. 0.09 divided by 4 is 0.0225. So now I got 15,000. Here I'm going to get 1 point this decimal raised to the 40th power minus 1 over the decimal without the 1 in front of it. So I'm going to add 1 here to make it 1.0225, raise it to the 40th power, and then minus 1. That's the bracket part. So I did it 1.0225 to the 40th power and then minus 1. I got the bracket part now. So now times 15,000 and divide by 0.0225. So this company will have almost $1 million in the account after 10 years. They'll have 956, 792, but there's a 6 here, so make that 793. This is how much they would have to work with. 956, 793. Almost $1 million. How much interest? Well, they paid 15,000 40 different times. This is how much they actually put into the thing. So 15,000 times 40 they paid $600,000, but they got almost $1 million after 10 years. So almost $400,000 of free interest money. So they got $356,793 in free money. So they didn't even have to pay it all themselves, is the nice thing. Okay, we're done with section 8.5. Got 100% there now. Save it. Okay, so 8.6 is about cars, and this is an application of annuities, because when you get a car, you in essence pay back the car in an annuity because you make monthly payments for a number of years. It's the same exact concept as an annuity. It's just a realistic example that most of us deal with in our lives. So they did a whole section about cars here. And notice the formula here looks a little different because you're solving for the payments here. You're not solving for the price of the car. So you borrow $17,000 for 5 years at 5% towards the purchase of a car. Use this formula. Payments equal P is the present value, and that's the $17,000. The car is worth $17,000 right at the time you're buying it. And then R over N, we've seen that before. And then here, now the reason this looks a little different is the future value of an annuity is what we just did. This is in essence the present value of an annuity. The price of the car is the present value of an annuity rather than the future value of it. So it makes things backwards. The 1 minus comes to the front instead of being in the back. And there's a negative in the exponent because of that. But the good news is you don't have to memorize the formulas anyway. Just whatever formula they say to use that one. You'll see the solving's pretty similar. Do not round to the final answer, then round to the nearest cent. Notice they switched to cents strangely, but when car payments, they want as much money as they can get out of you, so they do charge to the cent. Okay, so put the 17,000 where this P is. 5% or 0.05 is going to go in the 2 R slots. Cars and houses are almost always monthly, so you're almost always going to get an N of 12. And then car loans are usually 3, 4, 5, or 6 years. This one has 5 years, so that would be the T. And there's only 5 problems here just because these each take a while to do. So the car payment, and if you're ever going to get a car, you could use this formula right on the spot and figure out what your payment's going to be. So you do the present value of the car, that's what the P stands for. And then you have your R over N in the top, because that's what happens when you're solving for the payment. And then the bottom is kind of strange because it's backwards from what we were just doing. It has 1 minus, and then you get your usual 1 plus R over N. And then the exponent has a negative instead of just NT, it's negative NT. So this person wants to get a $17,000 car. The interest rate was 5%. Cars are always monthly, 12. 1 minus. So then we have 1 plus the same fraction. And then just include the negative there. The 12 always goes first. And they're doing this for 5 years. But pretty similar to the other problems. Do the exponent first. Just ignore the negative for a second. 12 times 5. Do that first. 12 times 5 is 60. So you're actually going to have negative 60 for that part, but I'll just write 60 here. Then your fraction, unfortunately with cars and houses, the decimals are going to start getting messy now because divided by 12 is not nice to work with. So 0.05 divided by 12, in fact we had that one in the previous section, that's this messy 0041666 repeating. Okay, so I could multiply this while it's on my screen. Since I have the whole thing on my screen, I'm just going to multiply by 17,000 right away, so I can get the top of the fraction done. And unfortunately, that's a messy answer too, which this is common with car payments. Okay, so I'm just going to write a rounded version of it, but then I'll put more decimals in later. 70.8333 repeating. 70.8333, yeah. Okay, so now I'm going to type this again here in this parenthesis part. See this 0.05 divided by 12? I'm going to type that again just so that I get the whole decimal without any rounding. That's 0.05 divided by 12. Now I'm going to add 1 to it. There's 1 point, whatever it is. And then you always do exponents next, so I need to raise it to the negative 60th power. So hit raise to, in this calculator I type 60, and then there's a plus minus button down here. So if I click that, then it makes it negative 60. Some calculators you type the negative first, then the 60. Here I have to type the 60 first, then the negative. Okay, so then I need 1 minus this answer, but I don't want to retype this whole thing. But 1 minus 0.77 should be a positive answer. So I'm going to intentionally do it backwards and hit -1 just so I don't have to retype that long decimal. And it'll wrongly be negative, but then I can hit my plus minus button to turn it positive, because that's what it should have been. So this should have been 0.2207 real long decimal. But I would like to have the 70.8333 divided by this, and I don't want to retype this one. So this is where I'm going to do this intentionally backwards too, and hit divided by 70.8, and just hit enough 3s till it goes across the screen. That's enough that rounding won't be an issue anymore. But this will be the backwards version of it, so that's when I need to hit this 1/x button. And you'll know if you're right, because see how can this be a car payment? Who would pay less than a penny for a car payment? Nobody. So if you hit 1/x, now that sounds like a car payment, $320.81. So you can usually tell if your answer is logical or not. If you're getting less than a penny or thousands and thousands of dollars, you probably did something wrong. So $320.18, that's the car payment, the monthly car payment. And you would do that for 5 years, every month. Does it say round up again? Round 2, okay. Round 2. 328. Oh, 81. I had a dyslexic moment. I put 18, but it was actually 81. 81. There we go. Okay, here comes the sad part, although it's not as bad with cars as it is with houses, but we'll be doing houses later. But you're going to pay this $320, and it was actually 81. I wrote it down wrong here too. You're going to pay $320.81 60 different times. Ignore the negative, just 60. If you make monthly payments for 5 years, you're going to pay 60 times. You're going to pay $320.81 60 times if you want a 5-year loan. This is how much money you're giving to the car company. You're just doing it slowly. You're giving them $19,248.60. But the car is only $17,000. So if you subtract the price of the car, that's how much interest you're paying. And remember how interest used to be free money for us? Now it's painful because we're having to give it to them. But this is the price for paying for a car and getting the car today. Your other option would be pay for the car for the next 5 years without using it, and then you would own the car. That would be the way to avoid interest payments. But most people that want to get a car, they need it now. They don't need it 5 years from now. So in order to have it now and not pay it off for 5 years, you're giving them an extra $2,000 for that privilege of having the car right away. And $2,000 isn't a whole lot when you're talking 5 years. It's not like you have to whip that out of your back pocket right now. And you'll see with houses, it's even worse with houses. If you get a $130,000 home, you'll pay like $500,000 in interest in 30-year loan. So, but unfortunately, most of us couldn't afford a house any other way. Okay, so now they're giving me one of these, which one's a better deal type of problem. I can get a new car that costs $30,000, and I can do a 4-year loan at 7.38%. Or there's a used cars option where the car is already 3 years old, so the initial cost is a lot less, $14,000. And then I'm still getting a 4-year loan, but they'll give me a lower interest rate because the car is not worth as much, and if I default on a loan, they won't be at much of a loss. So what's the difference in the monthly payments? Okay, so same formula. You're just going to do this. You're going to do problem number 1 twice and figure out the difference in the monthly payments. So the first monthly payment is the price of the car. Whoops, I should have just put a parenthesis here. Times R over N. And then the denominator's got 1 minus 1 plus R over N to the negative NT power. And we'll use this for both calculations here in this problem. So part A, there's a $30,000 new car. That one has a higher interest rate, 7.38. So 0.738. Unfortunately, cars are always monthly, so definitely N's going to be 12. But I get to have the same fraction here, 0.738 divided by 12 to the negative 12. And I think they were both 5 years. Was that the case? No, 4 years. They're both 4 years. Okay, do the exponent first. 12 times 4 is 48. So you're going to make monthly payments 48 different times. So I'm going to do the fraction part next. 0.0738 divided by 12. Oh, okay, so here's a case where divided by 12 it came out pretty nicely. 00615. 00615. That's convenient at least. Okay, so since that came out exactly, I'm going to do the bottom part first now. I'm going to add 1 to that, plus 1. Raise that to the negative 48th power. And then I need to 1 minus it, so I'm going to have to do it backwards and hit minus 1. But then I can take the negative away. So this is my denominator answer. 0.2549 4405 and then 14. If you do like 10 decimals, that should be enough if it's really long. And then for the top of the fraction is 30,000 times this decimal without the 1 in front of it. 00615. And then I can divide by 0.2549440514. So now you're going to have to pay $723.69 every month if you want to have that expensive car. That's option number 1. Or you can settle for a used car that only costs $14,000. And by doing that option, you also get a lower interest rate too, 583. So 0583. Hopefully that divides by 12 nicely. And then I should have put a closed bracket here, but okay. 1 minus 1 plus, same fraction, to the negative 12 times 4 still. So the exponent is still 48. So let's see, how does 0583, does that divide by 12 nicely? No, okay. So when it doesn't divide nicely, then I like to do the top of the fraction first. So I'm just going to hit times 14,000 right now. Although that's not very nice either. Okay, so 68, the top of the fraction, 68.01666 repeating. Okay, so then we do our 0583 divided by 12 again. So I can get that long, messy decimal. Add 1 to it. Raise it to the negative 48th power. That's this parenthesis part. I would like to do 1 minus it, but I'm going to hit minus 1, which is backwards. That's why it's coming out negative. So if I hit the plus minus button, that'll turn it back positive. That's the denominator. So then I'm going to divide backwards and hit divided by 68.016666 and hit a bunch of sixes. This is the backwards version of the answer. So if I 1 over x, that'll turn it into the correct answer. $327.70. See, that's quite a difference in monthly payments. So many average people can't afford $700 car payments every month. So you might not be able to get the car of your dreams, but here's the difference. $723.69 is the new car price monthly. Minus, we're looking for the difference, which is minus the $327 for the used car. It's almost a $400 difference. The new car is costing you more than double every month if you want to get that one. Or you could save this $400 for other expenses and take the used car. And you'll be paying a lower interest rate too. So the difference in the monthly payments is $395.96. Oops, okay. Oh, round to the nearest cent. Didn't I do that? $395.96. Car. Okay. Let's see how far off it is. Huh. See how it's off by just 3 cents. And see, this is where that rounding can be that can make a difference on doing these. So what you might have had to do, it might have been on both of them, but if it's only on one of them, I'm not sure. Okay, so 30,000 times 0738 divided by 12. This is the numerator, 184.5. Okay, the denominator should have been 0738 divided by 12 plus 1 raised to the negative 48th power. And then if I do 1 minus 1, that gives me the backwards version, so change it to plus. And then I'm going to type divided by 184.5, 1 over it. That's still coming out to 723.69. On this one, 14,000 times 0.0583 divided by 12. 6801,666. Yeah, I had that right. So 0583 divided by 12 plus 1. Whoops. Plus 1 raised to the negative 48th power. Minus 1, change it back to positive. Divide by, now it's going to come down to this. This must be where the issue is. Depending on how many 6s I put here. Put a few more this time. Well, see, that's too many then. Oh, no, see, that's the 3 cents right there. So that was it. I just didn't put enough 6s. So it's 327.70, not 0.73. See, I'm off by 3 cents, literally. So that's the lesson. Sometimes you have to get these wrong until you can see what they really wanted. And I did like 10 6s the first time, and that wasn't enough. And then I put like 15 or 20 of them the second time, and then it was enough. So that's always the issue here when you get these big messy decimals, unfortunately. So yeah, it would have been correct if I would have had that. 723.69 minus 327.70. That'll be the 99 cents instead of 96 cents that I had. So it's 395.99. 3 pennies. But they're going to count it wrong if you don't do it exactly to the penny. Okay, but at least you could see how to do that problem now. Okay, magic word of the day time. Since we're talking about cars here, let's have the magic word of the day be convertible. So the cars where you can put the top down, send me the magic word of the day for August 1st, convertible. Okay, we got 3 problems left here. Suppose you decided to buy a car for $28,635. You save $5,000 for a down payment. You can get a 4-year loan at 7.31%. Okay, so I know what's going on here. This problem is no different than number 1, except there's a down payment going on, which is actually a real common thing in real life too. So you want to get a $28,000 car. I could just repeat problem number 1 and figure out the monthly payment. But if I have already saved $5,000, I can give that to them now, and it's going to make the monthly payments a lot less. And it's also going to make what you pay in interest less too. So if you can afford to do this, it's always worthwhile to do that. And also the first day you drive the car off the lot, you actually own $5,000 worth of the car already. Okay, so that's the only thing different. You have to do the down payment, subtract that, and now do the rest the same. So we'll have to watch out for rounding issues again, but payment. So I'm only going to have to pay for this $23,000 now, not the $28,000. I'm getting a 7.31 interest rate, so 0.731. And then cars are always monthly. And then 1 minus, 1 plus, same fraction. To the negative, it's always going to be negative 12 when you're dealing with cars, and then times the number of years. They want 4-year car loan. So we'll get negative 48 again right here. This is supposed to be a 12, so negative 48. So let's see how bad the fraction is. How does 0.731 divide by 12? Does it do so nicely or not? Not. Okay, so then I'm going to add 1 for this part down here. Raise it to the negative 48th power. Minus 1 and flip the sign back to positive. That's the denominator. Now maybe I could do this. Let's see if I can open another one of these. Let me do two at once or not. Yeah, that helps. Okay. Okay, so there's the denominator right there. The numerator is 23,635 times 0.0731 divided by 12. There's the numerator. Whoops. So if I divide, I'm just going to retype this whole thing right here, even though it's kind of long. 252-867-69822-477-2623-913-846-853-48368. You probably don't need all those decimals, but we saw when I did like 8 or 10 of them, they counted it wrong. So just to be safe, I'm doing them all. Okay, so then your payment would be $569.37 every month. But if I hadn't done the down payment, it probably would have been like $700 again, like that other one that was a this one was a $30,000 car. $30,000 car had a $700 monthly payment. This is almost the same price right here. But because we did a down payment, we got the monthly payment down under $600 even. $569.37. So that's all that happened on 3 was the down payment makes the price of the car lower. And it'll make your monthly payment lower too. What's the total interest? Okay, so that's the same as always. You're going to pay this $569 48 times. That's how much money you're actually putting into this thing. $569.37 times 48. This will be larger than $23,000, but that's why you're getting the car now. $569.37 times 48. You're going to pay $27,329.76 over 4 years. But the car was only costing us $23,635 after our down payment. Right there. So this is how much interest there is. Almost $4,000 of interest because we're talking higher priced cars here. 3694.76. 3694.76. Yeah. So that's still done the same way. You're just doing it from the smaller amount. Okay, here they throw in some more realistic things. Suppose you drive a car 30,000 miles in a year and gas averages $4 a gallon. What will you save in annual fuel expenses by owning a hybrid car that averages 30 miles per gallon rather than an SUV that averages 9 miles per gallon? Okay, so if you drive 30,000 miles per year, and then you get 30 miles to the gallon in the hybrid car. You're driving 30,000 miles per year and you get 30 miles to the gallon. 30,000, I can close one of these now. Okay. 30,000 divided by 30, you will have to get 1,000 gallons of gas over the whole year. And it costs $4 per gallon, so you'll spend $4,000 in gas money. But if you get a gas guzzling SUV that only gets you 9 miles to the gallon, 9 miles per gallon, you're going to use a lot more gallons. 30,000 divided by 9, you're going to have to get 3,333.333 gallons of gas over a whole year. That's more than 3 times as many. And if I multiply by $4, now you're spending $13,333.33 on gas. You're spending almost $10,000 more on gas just because you want the cooler looking car, or maybe you need to load up a bunch of people in it. Round to the nearest dollar. Okay, so how much will you save? You'll save whatever these subtract to if you ignore the pennies. I wasn't sure if they wanted dollars or cents, but it says nearest dollar. So you'll save $9,333 by having that hybrid car. See, people don't take this into account when they buy cars. Plus, you're polluting the environment more with the SUV too. So now they're going to just relate something here that we learned previously. This is taking me back to the last section, 8.5. Here's an annuity. What if I took this monthly fuel savings at the end of each month and put it into an annuity that pays 5.2% compounded monthly? What will I have after 9 years if I do that? So you're saving $9,000 in a year's time. How much are you saving per month? So first you have to divide this by 12 to see the monthly fuel savings. Every month you're saving $777.75. So now go back to the annuity formula. Oops, NT minus 1 over R over N. And then this P right here is this 777.75. Okay, you're getting 5.2%. So 052 monthly. There's no negative in this exponent. They said do it for 9 years. And then same denominator fraction as the numerator. Nine years, yes, it says 9 years. I was just double checking. Okay, so 12 times 9 is the exponent. That's 108 times. And then the fraction, see how badly this divides out. 052 divided by 12. See how bad that one is? Okay. 004 and a bunch of threes. Okay, so now at least the top will be easier. If I leave this on the screen, I'm going to add 1. That gets me the parenthesis part. Raise it to the 108th power. And minus 1. Then multiply by 777.75 and divide by 004. I'm just going to a whole bunch of threes even off the screen a little bit. Then you can't go wrong if you do a bunch of them like that. So you will have 106,824. And there's a 0 after that. So if they want dollars, this is the answer. See, what this money represents is this is how much money you're giving to gas stations in order to have that SUV. Over a 9-year period of time, you'll just give $100,000 away to a gas station, to gas stations, by wanting to have an SUV over having a hybrid. Whoops, 106,824. So that was just a repeat of something we learned previously. Luckily, just a little bit of review there. So final question, if a 3-year car loan has the same interest rate as a 6-year car loan, how do the monthly payments and the total interest compare? Okay, so there's a double-edged sword here. If you want to have lower payments because you can't afford higher payments, one way to do that is to have the loan go for a longer period of time. So a 6-year loan is going to have lower payments than a 3-year loan if you keep everything else the same. But unfortunately, you're going to pay a lot more in interest by doing that. So it just comes down to what people can afford sometimes. But if you want to pay less interest, try to do it in less time. That's kind of the lesson here. So monthly payments for a 3-year car loan will be smaller than, less than a 6-year car loan. No, I said that wrong. Greater than. Sorry, greater than. Monthly payments for the 3-year car loan are greater, which is why most people can't do that. They can't afford it. But then the interest for the 3-year car loan will be less. So that's the double-edged sword. Do you want to save interest money? We'd all like to do that. But if you can't, like, think of that problem where it was $700 car payment or $300 car payment. If we could pay the $700, we're going to pay less interest, but a lot of us can't afford that, so some people don't have a choice. But that's what you're really doing with this. So less years is good for you in the interest side of it, but it's bad for you in the monthly payment. That's kind of the deal here. Okay, so it says I got an 80, but that's because I missed that one problem where I was off by a few pennies because I didn't put enough decimals in my calculator. So remember that. Do not round until the final answer, and I made the mistake myself, but anytime I make a minor mistake for you guys, at least you can see that, and hopefully you won't make the same mistake. So that is it for Tuesday, August 1st. We've done every problem in section 8.5 and 8.6 now. Tomorrow, August 2nd, we'll be doing the end of chapter 8, 8.7 and 8.8. And then on Thursday, we also cover the first 2 sections of chapter 11, which are not only easier problems, but they're a lot shorter than these too. So at least you'll have a few problems on the third test that are easier and shorter. So see you tomorrow for the end of chapter 8.